All right. So, today we are going to talk about adversarial search. And before I start, I do want to mention that as always, these slides have been not only prepared by me, I am standing on the shoulders of giants, and a lot of these slides came from Stuart Russell from UC Berkeley, and then several people actually improved them, like Linda Shapiro and other faculty members at University of Washington AI, and so on and so forth. I am also using some slides from Henry Kautz, who was an ex who is an ex AAAI president, a really famous researcher in the field of AI. He was the person who actually taught me the first AI course. So, a lot of what I do today is indebted to Henry Kautz, because he sort of got me excited about the field of AI. Okay. So, what do we want to do? So, we have we have done search algorithms, some of them, and I have repeatedly mentioned that the search algorithms that we are considering are single agent and atomic search formulation problems, and we are going to relax one of those. What are we going to relax? We are going to relax the single agent assumption here. We are going to play 2-player games in this class now, and games have been considered one of the foremost demonstrations of artificial intelligence. Why do AI researchers study game playing? I mean, it's sort of like toy problems. These are like, just fun things, playing chess or playing whatever game, tic-tac-toe, whatever. Why do AI researchers engage with these games? So, first of all, these games are actually, even for for a problem itself, these are good reasoning problems. They are formal problems, so they are easy to specify. The rules are well laid out. It's not like a robot is interacting in a physical environment where lots of things can go wrong. Suddenly it can rain, suddenly it can be sunny, suddenly somebody can come and punch the robot. That's a lot of complexity to deal with in one AI system. On the other hand, if you are thinking about chess or any such game like Othello or whatever, the rules of the game are fixed. You have 16 pieces on each side, and there are very specific ways in which they can execute, and so on and so forth. So, these are formal problems, right? These are problems which can be easily laid out in a formal abstract specification, and these are not easy problems. I mean, in fact, humans also think that if you are playing a game at a high quality, then you must be an intelligent person, right? So, therefore, these are good reasoning problems, and moreover, they allow direct comparison with humans. So, suppose I create a good AI system which is able to play this game, I can directly compete against humans, and in fact, that becomes my demonstration that my AI has achieved high quality of intelligence or superhuman performance and things like that. It's harder to do that in the context of, let's say, robot control and so on and so forth, but it's easier to do it in the context of a game, because we can play against, we can defeat, we can lose, we can draw, and things like that. So, what are the different kinds of games, right? What are the characteristics of the games? First of all, we all play moves, right? We make a move, we change a pawn and move it one step forward, and so on and so forth. And then our adversary, right, the person we are playing against, our opponent, also makes a move. Of course, these moves can be done simultaneously. There are some games where there is no notion of, I make a move, you make a move. Can you think of one such game where there is no sequentiality between adversaries? Racing? Sure, racing is one such game where there is no notion of, but in racing, really, if you think about it, our goal is to do as best as we can. I mean, there may be some strategy where we will come in front of the other person and not let them pass and things like that for like marathon kinds of games, but at least for the 400 meters, 800 meters and so on, there is a relatively straightforward thing that I want to just do as best as I can. Right? Rock, paper, scissors. Rock, paper, scissors is one of the games where I am playing against one adversary, but I am not making one move and then they are making their move. In fact, if you do that in rock, paper, scissors, I will always lose, right. So, then in addition to the sequence of moves, I will also have rules that specify what are the moves that are allowed and what moves are not allowed. A pawn can only go 1 or 2 steps depending upon whether it's a first move or later move. Also, if the pawn has to attack, then it can only attack obliquely, and so on and so forth, right. Now, the moves can bring you money or reward, right? And in the game of chess, there is no such reward per se, except if it's a timed chess that I am losing some time, but the reward comes at the very end based on whether I win, lose, or it's a draw, right? But there may be other games where each move gives me something back, right? And our objective will always be to optimize our reward or our payment, right? So, this is how we are going to formulate the various kinds of games, and there is one fundamental difference in which between what we have been studying so far, which are the various kinds of single agent search algorithms and an adversarial search algorithm, because in single agent search we have sort of made the assumption that when I take an action, I kind of know exactly where I reach, and later I am going to take the next action from the state that I reached in. That is why I can talk about sequence of steps, because all those steps are in my control. I have a goal to reach, I can do this action, I can change, have the gap go right, have the gap go left, or whatever it is in the n puzzle problem. But basically whatever moves I do, I can exactly know which state I am going to reach, and I know that I am going to be taking the next move from that particular state. Now, that completely changes in game playing. Why? Because I take an action, now it is not in my control anymore. I do not know what is going to happen next, because my adversary will be making their move, and they can make any move, and I have to be prepared to deal with whatever move they make, and also I should take the action that reduces their chances of winning or makes me win, but I can't think of it as a sequence of steps, because not easily, we will, but at least at the onset it does not feel like a simple sequence of steps kind of a problem, because after every action the control is lost and I do not know exactly what is going to happen. And moreover, in most problems there are some kind of time limits. So, we may not be able to reach till the very end when we are doing searching, right. So, in depth first search, breadth first search, and so on and so forth, we have sort of said that we can reach the goal and we will always output a solution to the goal. But now we will not be able to do this, as we will see in the lecture. What will happen is that we will not have the time to search till the end of the game. Game can take 80, 160, 200, 300 plays. I make a move, opponent makes a move, lots of these, and searching till this large depth is going to be extremely difficult, and so it is not going to be usually possible to find the goal when we are doing the searching. So, we will have to be approximating all the time, right. We are going to be talking about two-player sequential games where opponent makes a move, it creates a new board position or game position. We check whether the opponent has won or lost. If so, great, or if not, then we generate successors exactly like we used to do in atomic agent. So, we have now from this board position we will have many different possible actions. We will figure out for all these actions what are the different states we can reach, and then we will do something, we will evaluate these successors. And most of the magic will be how do I evaluate the successors, and then I will be taking the action which seems like the best successor, best action, and then I will repeat the process. So, this is how my two-player sequential game is going to go, right. And of course, as all of AI is search, we have discussed this a little bit, right. A lot of people think that AI is search. We are going to take the search view for this problem for now, and to us games will be some version of search, but we are going to call it adversarial search, because as I said, this is not exactly find me the sequence of steps, it is more like I take an action and now the control is lost. And so, for any kind of search algorithm, I need to have a state, an initial state, a terminal test, a successor function, and that is not very hard to figure out. Like we will have board configurations as states. Suppose we have like a board game, although if it is a different kind of game, then that configuration will be the state. The initial state would be the initial starting point of the game. A successor function would be what are all the actions that I or the adversary can take, indicating all the legal moves and the resulting states. Terminal test would be when the game is over, and also whether I won, the adversary won, or there was a draw, and there will be some kind of a utility function. And as a start, we will say that utility function would be -1, 0, +1, and -1 would indicate a loss, 0 would indicate a draw, and +1 would indicate that I won. Everybody okay with all of this? So, now let us think about this. So, first of all, we are trying to maximize my utility function. I want to get to +1, for example. Well, if I am trying to maximize my utility function, what is the opponent trying to do? You can always say that it is trying to maximize its utility function. But in this case, in this specific case, its utility function is, what is its utility function? With respect to my utility function, what is my adversary's utility function? It is negative. When I win, he or she, the adversary loses. When I lose, the adversary wins. Let us say the adversary is human and I am the computer, because we are thinking from the computer's point of view. So, I want myself to win, which basically also means I want the human to lose, and similarly the human wants the machine to lose and themselves to win. So, we could have defined two different utility functions and thought of a search algorithm which maximizes my utility in my turn and their utility in their turn, but I am going to simplify this and I am going to only think from the computer's point of view. But even then it is not that difficult a problem, because at any time I am making a move, I want to maximize my utility function, and any time the human is taking the move, the human wants to maximize the negative of my utility function, which is equal to saying minimize my utility function. So, you can think of this search problem in a very interesting way, where the states are ordered as max nodes and min nodes, and max nodes and min nodes, right. So, let us think about a search tree variation, search tree formulation. Let us say we will look at a simple problem of tic-tac-toe. The computer starts, the computer wants to put its cross and not its cross such that it maximizes its utility function, which is it wins. And then as it is thinking about what is going to happen next, it is going to say that the opponent is going to make their move, and their move would be such that my utility function is minimized. They do not want me to maximize my utility function, they want me to minimize my utility function. And so, this will be like a min node, and then I will get my turn and I will be a max node, and then they will get a turn and they will be the min node, and the game will keep on going. Eventually, we will reach the terminal state, a terminal state in which there is a row like this, where there are 3 knots in a row, and here where there is a draw and so on. And so, if there are 3 knots in a row, I have lost. So, the utility will be -1, if in this case it will be 0, and in this case it will be +1, and so on. And this search tree, believe it or not, has a name, and it is called the Minimax search tree. Not surprisingly, I am alternating min and max. So, in Minimax parlance, for whatever reason, we will not worry about it in this parlance, only in the game playing, a move has a special meaning. It is not I made a move, no. I take my action and that is called a ply, and then my opponent takes their action and that is called a ply, and together it is called a move, for whatever reasons, right. So, we will just learn this. And then a utility function would be the function applied at the leaves, and then we will be backing it up, and I will explain what backing it up means. See, backing it up means that if I played this action in the limit of the game finishing, what is the best or the worst utility this node is going to get. That will be the notion of backing up from the leaf back. See, because notice that at every step we are not getting anything. The final value, the final utility we are only getting at the end of the game, and we need to figure out what is the utility of taking my action now. So, I need to back up that value, back it up such that I know now what is the utility function of, what is the utility of taking this particular action. And a minimax procedure will search down levels, at the bottom level apply the utility function, back up all the way back to the root node, and the node will select the move. And in your mind, try to connect it with one of the depth first search, breadth first search kinds of algorithms, and see, we will talk about which algorithm it is, right. So, by the way, in this slides, I am going to say that a triangle sitting upright is a max node, and a triangle sitting vertically, the mirror image, right, opposite, is a min node. So, this is a max node at the top and this is the min node. And let us say it is a 3-step game, so, or 2-step game. I can take an action A1, A2, A3, my opponent can take actions, these different 9 actions depending upon which action I took, and then at the end I get some utility, and the utility values are shown at the bottom. So, now if I take action A1, what should my opponent do? Should it take A11, A12 or A13? So, here is a dumb question. If I decide to take A1, what should my opponent do? A11. Why? Because my opponent is minimizing, and I will, after they take A11, I will get 3, if they take A12, I will get 12, if they take A13, I will get 8, and they want to minimize my utility function. So, they will always take A11, and so what is my utility? Best utility, best, not best. What is, see, so, okay, there is one thing I do want to say before we move forward. You know, opponents can be terrible. Like if you are playing with a 3-year-old and you are playing tic-tac-toe, you know, you can defeat them sometimes. But if you are playing a computer which knows its stuff, can you defeat a computer in tic-tac-toe? No, the optimal play is a draw. For now, in this class, we are going to study the game between two optimal adversaries. I am as smart as I can be and my opponent is as smart as they can be. So, when I say what is the utility of A11, I am going to assume that after that, after I take A11, my opponent would do the best thing for them, which means the worst thing for me, and I will do the best thing for me and they will do the worst thing for me, and this game will go on until it reaches the end. So, when I ask the question what is the utility of A11, I will assume optimal play from there on. And in the world of optimal play, what is the utility of A1? What is the utility of A1? 3. Because after that I know that if I took A1, my opponent is going to take A11 and I am going to get 3. Similarly, what is the utility of A2? So, when I take A2, what will my opponent do? A21, and the utility of A2 would be 2. And similarly, if I took A3, my opponent will take A23 and the utility of A3 would be 2. So, now what should I do at the top? What should I do at the top? Any confusion in this? We should do A1, I should do A1. Why should I do A1? Because I know that I can force my opponent to a move which gives me 3 as my final utility, as opposed to taking A2 or A3, in which case I can only force my opponent to give me 2, right, if they are playing smartly, and so I will take the one that maximizes my utility function. So, now do you see the meaning of backing up the values? These values are at the leaves, but they are being backed up to intermediate nodes based on whether it is a max node or a min node. At the top, I figure out what is my utility at the top and which action is the best. And in fact, not only do I know the best action, I also know the best action of my adversary and my best action and the adversary's best action up to the very end of the game.